Hi there, welcome to the demonstration of our product CAN Protocol Learning Kit. This product comes as a package containing hardware and the software parts. The hardware part of the package consists of two numbers of vCAN Unimod, which are the configurable universal CAN modules, two numbers of Unimod evaluation boards, which are the base boards or the carrier boards for the above CAN modules, power adapters, vCAN CAN bus analyzer hardware, and an optional ST-Link debugger. Let me quickly show you the hardware contents. So this is the vCAN Unimod configurable CAN module. This is the vCAN Unimod evaluation board, which is the base board for this module. We have here the vCAN CAN bus analyzer hardware. We have the power adapter, and we also have the ST-Link debugger, which is the optional part of the package. The software part of the package comes in a DVD, and it consists of the following: the Unimod configuration tool, which is the GUI based tool to configure the Unimod modules, vCAN application software, which is the GUI based software for the CAN bus analyzer, code limited version of IR embedded workbench, IDE, serial bootloader utility to download or flash the modules, CAN modules with the desired image files, and finally a sample CAN application source code in the form of IR embedded workbench project written in embedded C. So let me quickly show you the contents of the DVD. So this is the Unimod configuration utility. So here is the IR embedded workbench code limited version installer. This is the vCAN application software, the serial bootloader utility, and we also have the necessary hardware drivers. So this CAN protocol self-learning kit can be used to learn and practice CAN protocol in two parts. In part 1, the user can build and analyze the CAN network through configurable modules, that is, the vCAN Unimod modules in this approach will be used as configurable modules where they have the default inbuilt firmware within them along with which they are shipped. So here there is no need of developing any custom code or embedded firmware for these modules. They already have the firmware built into it at the time of shipping. So the user just need to configure these modules according to his requirement and build and analyze the CAN network. So this is more suitable for system level engineers or electrical engineers who want to explore the CAN protocol and learn the CAN protocol without getting into the coding or firmware development part of it. Then this kit can be used as part 2, where the user can build and analyze his CAN network by using the vCAN Unimod modules now as programmable modules. So here the user will be developing custom code or firmware for each of these modules as per his network requirement and then form the desired CAN network. So as mentioned, part 1 is the configurable approach where the CAN modules will already have the inbuilt default firmware with which they are shipped with. So this learning process can be categorized into the following steps. Step 1 is the planning of the network, planning the desired CAN network. Step 2 is configuring each module as per the above planned requirement. Then step 3 is interconnecting these modules, testing the network, and then finally analyzing the network using CAN bus analyzer tool. Then we'll move on to the part 2, which is the programmable approach. So here the user will develop custom firmware by himself, the starting point of which is the sample CAN application source code delivered in the DVD for each of the CAN module using embedded C coding. So here again the steps can be listed as: step 1 is planning the desired network, step 2 is customizing the sample CAN application source code according to the user requirement based on the above plan, then interconnecting the modules to form the network, testing the CAN network, then finally again analyzing the network using the CAN bus analyzer tool. So let us get started with the part 1, which is the configurable approach. So here we need to plan our desired network. So in my case, I want to build a simple CAN network made up of 2 nodes. For each node I'll be using one of these configurable CAN modules. So in node 1 I want to have one analog input, for which I will be using one of the onboard potentiometers to generate the analog signal. Then I want to have 8 digital inputs, for which I will be using the onboard dip switches to feed the digital input signals. And I want one analog output, for which I'll be using onboard LED intensity variation. Then I want 8 digital outputs, for which I will be using onboard LEDs to observe the digital outputs. So similarly, I want to use the other module to form the node 2, which will again have the same number of analog input and outputs. Then I want to interconnect these two modules using the CAN bus. So you can see here, these two wires represent my CAN high and CAN low wires. So coming to the CAN messages part of my requirement, I want these two nodes to exchange a pair of CAN messages between them. So the node 1 will have two outgoing CAN messages with message IDs 3A1 and 3D1, which will act as the incoming CAN messages for the other node. So the message ID 3A1 will carry the analog input information, that is potentiometer value, in one of its bytes as an outgoing CAN message. Similarly, the outgoing message 3D1 will carry the dip switch status information in one of its bytes. Similarly, the node 2 will generate two outgoing CAN messages with IDs 4A1 and 4D1, carrying analog potentiometer and dip switch information to the other node. So 4A1 and 4D1 messages will act as incoming CAN messages for node 1. So this is the network I want to build and test. So we'll now move on to the step 2. To achieve the above network, I need to first configure each of these modules according to my above requirement. For this, I'm going to use the Unimod configuration tool. So if the Unimod configuration utility is successfully installed, you will have a shortcut, CAN Unimod. So if you invoke the utility, it will open up like this. So since the hardware we are using is the CAN protocol self-learning kit, we have to select the CAN learning kit option. So it will enable the appropriate tabs. As you can see here, it is loading the appropriate tabs. So you can see it will have incoming and outgoing CAN messages in this tab, where you can set even the CAN baud rate. Then there is tabs for digital inputs, 8 digital inputs, 8 analog inputs, 2 analog outputs, and 8 digital outputs. So these are the supported input outputs in this hardware. So to save time, I have already invoked 2 instances of this Unimod configuration tool to configure the 2 hardwares. So these are the 2 instances. So this instance is to configure the first module, and this instance of the GUI tool to configure the second module. So to save time here in this demo, I have already configured both the instances corresponding to the requirements of the 2 modules. So let me quickly show you the configurations that I have done for the first module. So you can see here I have listed 2 outgoing CAN messages with IDs 3A1 and 3D1, which will be transmitted at a periodic rate of 1 second. The payload length for 3A1 is 4 bytes, 3D1 is 8 bytes. Similarly, I have listed 2 incoming CAN messages with IDs 4A1 and 4D1. This is what we planned for the node 1 or the module 1. And I'm going to use a CAN baud rate of 500 kbps in my demo. So now I want the outgoing CAN messages to carry the potentiometer information on one message. So I have configured the same in the analog input tab. As you can see here, I am using the third analog input channel out of the 8 available to me in my hardware, so that I can use the third potentiometer on board of my hardware. I have linked it with the CAN message ID 3A1, and the potentiometer information, the ADC information will be of length 8 bits, which is transmitted on byte 1, starting from bit 1 in the message outgoing message ID 3A1. Similarly, I want the dip switch information, that is digital input information on my first hardware, first module, to be transmitted on the outgoing CAN message 3D1. So I have configured the same in this digital input tab. I have enabled 8 digital inputs available to me on board. I have linked all of them to outgoing CAN message 3D1. So this 8-bit information will be going on byte position 8, byte number 8 of the CAN message. Each bit will carry one digital inputs, that is one dip switch status. So similarly, for the incoming CAN messages, that is 4A1 and 4D1, I want them to be shown on as analog outputs and digital outputs in my hardware. So I have two analog outputs. So I'm using the first analog output channel to show the content of the incoming CAN message 4A1. I know the message will be, the other module analog information will be coming on byte 1 of this message. So I have configured it accordingly, and it will be of length 8 bits. Similarly, the incoming CAN message 4D1, which will provide me the dip switch information of the other hardware, I want to output them on the onboard LEDs. So I have enabled 8 digital outputs available to me, linked it with the incoming CAN message 4D1. I know the information is available to me in byte 8, and each bit represents one dip switch status. So I am outputting them to 8 LEDs as digital outputs. So I have configured two outgoing CAN messages, two incoming CAN messages, and I have linked them with digital inputs, analog inputs and outputs as per my requirement. Now the next step is to download these configuration settings to my first module. For this, I'm going to use the USB to serial converter, as you can see here. This is the USB to serial converter. I have plugged it to my hardware. Now I want to power up the hardware. You can see both the modules start in normal mode, as can be observed by the normal blinking of the module LEDs, the screen LEDs. Now I want to put the module 1 into the configuration mode to download the settings, for which I'm going to short the jumper pins on the module. So I'm going to short the jumper using this jumper, and I'm going to apply a reset. You can see the LED blinking stops, indicating that this module has entered into config mode. The other module is still in the normal mode, for which we are not downloading any settings. So as of now, we are downloading the settings for this module. So this is successfully placed in the config mode. I'll go back to my GUI. Now I want to find my COM port. So it has been detected, my USB to serial adapter has been detected on COM3. So I'm going to select COM3, and I'm going to connect to the hardware. So hardware has been successfully connected. So the next is to start sending my configuration data to the module. Now you can see, as the configuration settings data is sent to the hardware, the LED, onboard LED, starts blinking at a very slow rate as and when it receives the packets, configuration packets. So this slow blinking LED on the module indicates that it is successfully being configured. So the configuration is in progress. You can notice the other module is still in the normal mode because we have not placed it in the configuration mode. So let us wait for the configuration data to be completely downloaded into this module. As the configuration data is being downloaded, let me quickly show you the configuration settings that I have done for the second module. That I have already done the settings in this instance of the GUI. So the second instance of the GUI I have already configured for the second module. So I have listed two outgoing CAN messages 4A1 and 4D1 transmitted at a periodic rate of 1 second, and two incoming CAN messages 3A1 and 3D1. This is exactly the opposite of the other settings that I made earlier for the first module. So these are the incoming outgoing messages for the second module. I am using the same baud rate of 500 kbps, and I have linked the analog input information to be transmitted on message ID 4A1 in byte 1 of length 8, and the 8 digital inputs, the dip switch status, I have linked to outgoing CAN message 4D1 in byte 8, each bit representing one pin dip switch. Similarly, the incoming CAN messages are 3A1, which I have used the output on the onboard LED for LED intensity variation. And similarly, the incoming CAN message 3D1 has been linked with onboard digital outputs, which can be observed on onboard LEDs. And this information will be available on byte 8, each bit representing one pin status. So I have made the settings ready for the second module, which will act as node 2 in my network. So let me come back to the configuration of the first module. You can notice the configuration has been downloaded successfully, and LED is not blinking anymore as configuration LED. So let me release the connection. I will unplug the USB to serial converter. I will release the jumper to put back the module into the normal mode. I just reset after releasing the jumper. You can notice the LED now starts blinking at a normal rate, indicating this the module has come back to the normal mode of operation. So both the modules are now in normal mode of operation. I now need to download the settings I have made for the second module. So this is the settings for the second module. To save time in this demo, I have already downloaded the settings to the second module previously. So the settings are already there in this module. So now we'll move to the next step, that is making our CAN network and testing the same. So I have to interconnect the two modules to form my network and then start testing of the network. So let me show you the CAN connections. So these are the two CAN wires, CAN high and CAN low. I have connected to CAN high and CAN low pins of the two modules. So both the CAN high and CAN low pins have been shorted between the two hardwares. So the two modules are now ready to communicate using the CAN bus. So if it is successfully communicating, then I will be able to see the dip switch information variation. So as I operate the dip switches on one module, you can see the LEDs turning on and off on the other module. So let me turn on few more LEDs on one module. You can see the LEDs coming up on the other module because this module is conveying this information on one of the CAN messages. Similarly, if I vary the potentiometer on this module, you can notice the LED intensity variation on the other module. Let me enlarge this video. So as I vary the potentiometer in one module, you can observe the yellow LED here as I vary the potentiometer, because one module is sending this analog input information to the other module through its CAN message. So we have successfully configured the modules to make a two-node CAN network, and we are able to see that they're exchanging the messages according to our configuration. So the next step is to analyze this network using CAN bus analyzer tool, which will enable us to observe the CAN messages being exchanged visually. So for this, and this is the canvas analyzer hardware. I'm going to plug this to my CAN network and start observing the CAN messages. So for that I need to invoke the vCAN application software. So if you have installed the drivers and the vCAN application software, you will have the icon created on your desktop. So if you invoke, the application will invoke as shown here. So let me make connection and start the network. So you can see I have connected my canvas analyzer to CAN high and CAN low pins on the network as shown here. Yeah, you can see. So if I put it into list mode, you can see the 4 messages which are flowing on the network. So to make it to visualize easily, we can put into the overwrite mode. So you can see the 4 messages are getting updated. So as I vary the potentiometer on one module, you can observe the message ID with 3A1, byte number 1 changing in its value. And you can also notice in the hardware the LED intensity variation, the yellow LED. So you can observe this byte value changing as I turn the potentiometer. And correspondingly the yellow LED intensity keeps varying. So if I operate the dip switch on one module, you can see the byte number 8 of the message 4D1 will be changing. Just keep observing this value, and simultaneously the LEDs, blue LEDs will be operating on the hardware. So we can use the canvas analyzer to analyze our CAN messages. We can also use this canvas analyzer to create messages and transmit into our network. You can notice that in canvas analyzer I have configured the same baud rate of 500 kbps for which I have been using in my network. The various features of our tool vCAN canvas analyzer has been captured in a separate demo video and is available on our website. So coming back to our presentation, so we have successfully completed all the steps in the part 1, that is the configurable approach. We were able to build our network, we were able to configure the modules according to our requirement, we were able to interconnect the modules and see that our modules were exchanging the messages on canvas, and finally we analyzed the network using vCAN canvas analyzer tool. So you might have noticed we did not do any embedded coding or firmware development in this approach. So this is suitable for system level and electrical engineers who don't want to get into the coding part of it, but still want to explore and learn the CAN protocol. Now for those people who want to go further one level down and do some coding in this kit, then they can continue with the programmable approach. So here again we will be planning the network as I have shown here. Then we will customize the sample source code delivered as part of the package to modify according to their requirement. Then download that code into the modules using the ST-Link debugger. I'm showing the ST-Link debugger, and then interconnect the modules, test the network, and finally analyze the network again using vCAN canvas analyzer tool. So for this approach, the code limited version of IR embedded workbench is given as part of the DVD. So this is about our product CAN protocol self-learning kit or CAN training kit. For more details about this product and also our various other products, please visit tangent-technolabs.com. You can also reach us at contact@tangent-technolabs.com. Thanks for watching this video. Bye bye.